I'm going to prove that n to the 5 minus n is divisible by 30, where n is an integer. So let's write this out. We want to show that 30 divides n to the 5 minus n for all n in the integers. Okay. So what can we observe from this expression n to the 5 minus n? Well, let's start by taking a factor out. So we could rewrite n to the 5 minus n as n to the 4 minus 1. And we could factor this further as n squared plus 1 n squared minus 1. So we're using a difference of 2 squares and splitting it up that way. And then we could use that again for this factor here. We could rewrite it as n minus 1, n plus 1, and leave the squared factor of n squared plus 1. Okay, so the way we're going to do this is by showing divisibility by other factors smaller than 30, and then using a result to show that the whole expression is divisible by 30. So let's first consider the factors n and n plus 1, right? So these two here. Doesn't really matter which pair among these three we choose for this first bit. Or actually it does, so long as they're not more than 2 apart. So we're considering the factors n and n plus 1. What do we notice about these two factors? That they're consecutive, and so for any number n, you take the next one. So this guarantees that one of them must be even. So one must be even, right? Whether it's n or n plus 1. So this implies, so if something is even, it means it's divisible by 2, right? So if one of them is divisible by 2, then the product n plus 1 must be divisible by 2 as well. So we could just jump straight into that step. So n plus 1 is divisible by 2. And because this pair of factors is part of these factors here, we say that the whole expression of n to the 5 minus n is also divisible by 2. Okay. So that's showing divisibility by 2, right? So next, let's consider a trio of factors. Take these three, and we're going to use the consecutivity of those factors, or of those numbers. So now consider the factors. So let's do them in order: n minus 1, n plus 1. In the same way, they're consecutive, starting from n minus 1 up to n plus 1. So what can we observe from this? one of them must be divisible by 3. We're taking 3 consecutive integers. That guarantees that one of them is divisible by 3. So 1 must be divisible by 3. So in the same way, you take the factors together, so n minus 1, n plus 1 is divisible by 3. Which implies that the whole expression of n to the 5 minus n is also divisible by 3. Okay. So this bit shows divisibility of 2, divisibility of 3. Now let's show divisibility of 5, and we'll see why we need to show divisibility of all those 3 numbers to show divisibility by 30. So let's show divisibility by 5. So for n is 0, 1, 2, 3, and 4. So there are 5 numbers here. And we want to take them in mod 5. So if you consider the expression n to the 5 minus n in mod 5, let's look at all, let's make substitutions of all these values of n and look at the result in mod 5. And if we get that for each substitution from 0 to 4 in mod 5 or into the expression n to the 5 minus n, if that results in 0, then we've exhausted all the cases in mod 5 and we've shown divisibility by 5. So let's consider 0 to the 5. So, I mean, you can do this, take the whole thing in mod 30, do all the cases up to that point from 0 to 29. It takes a while, so that's why we've split this up so that this last result we're just showing divisibility by 5, so we're only doing 5 cases here. So 0 to the 5 minus 0, so we're just making the substitution of 0 into this expression here. 0 to the 5 minus 0 is just 0. So that's good. So 1 to the 5 minus 1 gives 1 minus 1, which is 0. We're happy. 2 to the 5 minus 2 is 32 minus 2, which is just 30, which is congruent to 0 in mod 5, right? We're working in mod 5. 3 to the 5 minus 3 equals 243 minus 3, which equals 240. Again, congruent to 0 in mod 5. And finally, for the last case, making the substitution of 4 into the expression, we get 4 to the 5 minus 4 equals 1024 minus 4, which equals 1020, congruent to 0 in mod 5. Right? So this implies that the expression n to the 5 minus n is congruent to 0 in mod 5. In other words, the expression n to the 5 minus n is divisible by 5. We have an alternate way of proving divisibility by 5, it uses a theorem, namely Fermat's Little theorem. So I'll just do it as an aside here. So you could say alternatively, we could use Fermat's, so I'll just state this in a moment, Little theorem, which says that for any prime value p, if you take a, where a is an integer, raised to that power, that prime power, a to the p is congruent to a in mod p. That's just the theorem stated, where a is an integer. Okay. So using this theorem in the context we have, since clearly 5 is prime, we can let, in this case, a to be our n, or n to be the a here. We can let a to equal n, and then we get n to the p, which is 5, is congruent to n in mod p, so mod 5. Subtracting n on both sides, we get n to the 5 minus n is congruent to 0 in mod 5. And immediately we get the result that we have here, which implying the expression is divisible by 5. So yeah, that's another route we can take. Probably a better route in this case. But the other thing is that we're not always going to get prime factors. In this case we do. So we can use Fermat's Little theorem. So now we've shown divisibility by 2, 3, and 5. So what can we say? So since the expression n to the 5 minus n is divisible by 2, 3, and 5, and these numbers well, what are they? They're, if you look at them pairwise, they are coprime, right? So they are pairwise coprime. Then you could say that the expression is divisible by the total product. So then n to the 5 minus n is divisible by their total product. Right? And if you take the product of 2, 3, and 5, you get 30. And this is why we've split it up in this way. So this implies that n to the 5 minus n is divisible by 30. And that's what we want to show. So 30 divides n to the 5 minus n for all n in the integers.